It's time. Welcome back, everybody. I hope you had a good weekend. And we do have homework for tomorrow, so check it out. Any questions, thoughts about that? No. Great. Let's continue talking about grammars then. At the end last time we were talking about how to convert an NFA into a grammar. I thought let's just do another example just so we have our refreshed our memory here. How about, this is my favorite NFA for, well actually it's a DFA, but it doesn't matter, for binary numbers that are divisible by 3. I'm going to give names to the states just because that you need to in order to convert it to a grammar. So that's the, it's a DFA, but it doesn't matter, it's an NFA also. It's an NFA to convert, or to tell whether or not a binary string represents a number that's divisible by 3. And I hope you maybe have a vague memory of how we did this. I want to convert this to a grammar, and the way to do it is, it's very simple if you just remember how to do it. Convert to a grammar. So each state becomes a non-terminal symbol. Those are usually what we use the capital letters for in a grammar. So each state becomes a non-terminal, and each arrow or transition in the diagram becomes a grammar arrow, or production is what they're called in a grammar. Production. All right, so in this particular example, it's going to be S. S is always what I'm going to call the starting grammar symbol, the starting non-terminal symbol. And S has an arrow going back to itself labeled with a 0. And the way you encode that in a grammar is just S goes to 0S. And then there's also an arrow with a 1 to the T, and that will look like S goes to 1T. So each arrow translates directly as a grammar production. Generally speaking, the way this works is if I have an arrow on the NFA like that, this becomes the grammar production X goes to AY. All right. So those are the arrows for the S, and then the T arrows. You just look up here. Where do the T arrows go? I can go T to R with a 0. That would be T goes to 0R. Or I can go T to S with a 1. That would be T goes to 1S. And then finally R. The arrows for R on the original diagram are 0 goes to T, so this becomes R goes to 0T. Or R with a 1, R goes to 1R. Like so. All right, and this is almost done. The only remaining thing is, one thing I have not indicated in the grammar that is in the diagram is which states are accepting. So S is an accepting state, and when you're doing this conversion to grammars, the way you indicate that is just do or epsilon. In a grammar, an epsilon is sort of how you finish the grammar derivation by finally sort of de-substituting all of the capital letters that remain by turning them to epsilon. So that's why this is the starting state. Or this is not the starting state. This is what you do with an accepting state. All right, maybe I'll write that in my list here. Each accepting state gets a, production going to epsilon. All right. Could we just sort of convince ourselves, why does this grammar actually do what I want to do? So in this particular example, maybe I will, just so I don't have to scroll here, I'm going to bring this guy down. In this particular example, an example of a string that's accepted would be something like 0, 1, 0, 0, 1. This is accepted on the NFA, right? Because you can go 0 here, 1, 0, 0, 1, and that's it. All right, so this is accepted just by following the arrows around. And can I make a derivation using my grammar? A grammar derivation should just follow the arrows. Now I have you'll see what I mean by that. You have to begin with S, right? The grammar derivation always begins with the starting symbol S. Now, in my grammar, there are actually 3 different things that the S could become. What I mean by just follow the arrows is think about how you would do this string on this DFA and then follow those same arrows. So if I'm trying to get this on the DFA, I need to do the 0 first. So I'm going to do S goes to 0S first. Next, from here, I would follow the 1 arrow. So I'm going to do that here, which goes S goes to 1T. So now it says 0, 1T, right? The 0 was there before. I turned the S into 1T. And then what? Again, think about what would I have done next on the NFA to accept this string. I already did the 0 and the 1. Then the 0 next would go over to the R. So this is going to become 0, 1, 0, R. All right. Then the next 0, I have to go back to the T. So this becomes 0, 1, 0, 0, T. And then finally, the 1 at the end, I will go this arrow here. Oh, sorry. This arrow here, T goes to S with a 1. So this is 0, 1, 0, 0, 1, S. Right? T goes to 1S. And then finally, to finish it off, I go S goes to epsilon. And we're done. We have no more non-terminal symbols. So this is 0, 1, 0, 0, 1, the end. All right. You can see the grammar, the way that you think of these two things on the NFA versus the grammar are kind of backwards or kind of inverses or something, because at least when I think of the NFA, I think of we start with the whole string and then we kind of read the letters one by one, and the NFA sort of eats the letters one at a time until you get to the end. The grammar is kind of the opposite. You start from nothing in the grammar, and you build the string one letter at a time. But it's the same thing, because these grammar arrows are really doing the same thing that these NFA arrows are doing. All right. Any thoughts about that? This is fairly straightforward. I think you just have to remember how to translate from the NFA to the grammar. All right. So what this means is any NFA can be converted into a grammar. To say this in a more sort of interesting theoretical statement, this means that any language of any NFA can also be the language of a grammar. So I'm going to write that as a theorem. Any language of an NFA, of course, that means a regular language. That's what a regular language is. So the theorem is just that any regular language can be expressed by a grammar. Right? And the way you do it is you make an NFA first, and then you convert that into a grammar by the simple procedure that we just talked about. All right? Any regular language can be expressed by a grammar. That's because you just do the NFA, NA, and then you convert it into a grammar. Right? What about the other way around? Can I convert a grammar into an NFA? The answer in general is no, because we've already seen there are some grammars that make non-regular languages. So you have no hope of converting those ones into NFAs. But I mean, sometimes you can go the other way around. So I will just say sometimes we can convert sort of back the other way, grammar to NFA. But this is not always going to work. It cannot always work because some grammars make non-regular language, which would be impossible to convert into an NFA. But sometimes we can. For example, here's a real simple example. If it just so happens that the grammar looks like something that you could have gotten from an NFA, for instance this, all right, This grammar actually looks like one that you got from an NFA because every arrow looks like some non-terminal goes to like a little letter followed by a big letter. Actually, this can be translated directly back into an NFA. This looks like it came from an NFA, and we can reconstruct the original NFA, right? Apparently, it has two states, the S and the T, and then can we just sort of, let's see if we can just draw the arrows in. You know, S will be the starting state just because S is the starting symbol for the grammar. What about the arrows? I see an arrow here, S goes to AS. What does that look like on the NFA? Yeah.
An arrow pointing to S.
Yeah, an arrow looping back to S labeled with an A. All right. And then we also have S goes to BT. That will be an arrow from S to T with a B. All right. So those are the lines or the arrows from the first line. And then the second one we can read similarly. S goes to T. T goes to AS. That is an arrow back this way with an A. Then T goes to BT. That's a looping arrow here with a B. T goes to S. That's a little strange. Anyone want to suggest how I can interpret that? I'm used to seeing a letter there before the S. But yeah? Yeah, how about epsilon, right? So T, I think of this, when you see that, you sort of imagine this as like epsilon S, right? And I can make an arrow labeled with an epsilon. That will be an arrow from T back to S labeled with an epsilon, which actually is like this, right? I already had an arrow from T to S, so it's like that. And then finally, this or epsilon, how do I indicate that on the diagram? Yeah?
Marked is accepting.
Yeah, it means that T is an accepting state, right? This doesn't actually indicate any kind of arrow. It just means that T is an accepting state. There you go. All right, so in very simple situations, you can convert a grammar back into an NFA. Although, like I said, this is not generally possible to do. It's not possible in all cases, but in some cases it is. All right. I got one. You can do this with slightly fancier ones. Slightly fancier. I got one of these, and then I got one for you to try. How about this one? S goes to A, B, A, S, or A, T. T goes to A, A, T, or S, or epsilon. So this looks kind of like that other one, only some of the productions here don't just have one letter in front. They have several letters like this, A, B, A, S. All right. Anyway, there's going to be two states, right? The S and the T. And the S is the starting state. I can start off like that. S goes to A, B, A, S. I don't know about that one. Actually, the other one is easy enough, right? S goes to A, T. That is just going to look like this, as we're used to, right? How about I do A, B, A, S? Now, you may be tempted to say something, can't you just do like that? S goes to A, B, A, S will be something like that. The answer is no, you can't just do something like that because that's not allowed in an NFA. You can't label an arrow with a string, right? Every arrow must be labeled with a letter or epsilon. But we can kind of fake it. Rather than this, which is not allowed, all I want to say is if you start at S, you can get back there after doing A and then B and then A. So in order to make that happen on the diagram, I'm going to invent two extra states and just go like this, A, B, A. All right? You can give those states names if you want to, although it's not necessary. So that thing that I did down there is an attempt to simulate sort of what I wanted to do before, but was illegal that I crossed out. All right. So that handles S goes to A, B, A, S. All right. S goes to A, T is already done right there. T goes to A, A, T. I'm going to do the same kind of trick. Invent a new state. Actually, I think you only need one new state, and you go over that with an A, and then come back with an A. So for that, I'm going to make a new state here. A, like so. So now T goes back to itself after doing A followed by A. All right, we also have t goes to s. That is just one of these with an epsilon, right? And then t goes to epsilon indicates that t is an accepting state. So I say like that. There we are. All right. Any thoughts about that? How about this? Can I make it slightly fancier? What about instead of or epsilon? I'll just add on to it. How about also BAA? So T can just turn into BAA. You'll notice there's no other like capital letter here. So this is another way. We think of the epsilon as how you finish, right? When you do the epsilon transition, it means you're done, which is why the T is accepting. So you can just finish at T, or another way to finish is by, when you're in T, by doing BAA. Anybody want to suggest how I could indicate that on the diagram? If you're at T, you can finish just by stopping entirely, that's the epsilon, or you can finish by doing BAA at the end. Yeah?
Could you invent 2 more states and make one of them accepting?
Yeah, I like that. So the idea is like this, BAA. I think actually you need 3 more states. All right? So if you're in state T, you can finish the derivation by doing nothing. That's why T is accepting. Or you can finish the derivation by doing BAA at the end, which is this, right? From here, you can go B, then A, and it will be accepted. All right? So these are simple tricks. You still can't convert any grammar you want to an NFA, but if it looks like this, which is to say basically you have terminal letters, that is the little ones, followed by a single non-terminal. If it always looks like that, then you can always make it into an NFA. All right? I got one for you to try, and then we will move on to something a little different. How about make an NFA for S goes to ABS or BT. T goes to BBAS or AR or B squared. And R goes to BS or ABT or epsilon. See what you think. I'll give you a few moments. This will involve similar tricks. Start with S and T and R as states, and you're going to have to invent some other ones, little bitty ones.
Sorry.
Looks like people are doing pretty good. Let's talk about them. So I go S goes to ABS. That means from here you can get back to S after doing A followed by B. I need to invent a new state for that, just so that I can go A and then B back to S. So I hope you did something like that. S goes to BT. That's just an arrow like that. That's easy enough. And now T goes to BBAS. So for that, I need to invent some more states. I want to go T back to S after doing BBA. So I think I need two more states. BBA, like that. All right. And then T goes to AR. That's just a single arrow like this. T goes to AR. And then I have T goes to B squared. This again is this is indicating an accepting state from T. It can be accepted after you do B squared. So you make a new state like this. So from T, it can be accepted after doing B squared. Yeah.
How come you couldn't circle the second B when you were going from T to X?
All right. Yeah, you could notice that I already have a B and then a B here. So I believe it's the same if I were to just make that an accepting state. Yeah, that's true. To me, it's a little clearer to write it this way, but yeah, if you happen to notice that, I think that is correct. All right, okay, and then the R arrows. R goes to BS, that's just a single arrow here. R goes to ABT, that means this. R goes to ABT like that. So I can go from R to T by doing A followed by B. And then R goes to epsilon, what does that mean? I see some people are giving me the signal that means R is an accepting state. Yeah. R goes to epsilon means you can just finish by sitting at R. All right, excellent. I hope you got something that looks like that. Your picture probably looks different from mine, but great. Any questions about that? So the moral of the story is sometimes you can convert from a grammar back into an NFA, although it's only in very specific, a very specific format. Basically, the format has to be something like a bunch of terminals, that is the little letters, followed by a single non-terminal, or maybe followed by nothing. Then that you can handle that also. All right. Excellent. Let's talk then about other kinds of languages you can make with a grammar that are not regular languages. We've seen a couple examples of this already, but I want to talk in more detail about this. It turns out actually it's difficult to talk about all possible grammar languages at once, just because there are many different kinds of formats for grammars. Actually, there's a name for this kind of format. What I said of all terminals followed by a single non-terminal. This is called a right linear grammar. Right meaning the non-terminal always appears on the right. There's also a left linear grammar, which actually is harder to convert into an NFA, but it is still possible to do. And there are many different classifications of different structures, different types of grammars. To talk about all grammars without any kind of requirements on the structure is actually very difficult. There's a very important type of class of grammars that we're going to be talking about in quite a bit of detail, and that is called the context-free grammars. So rather than trying to consider any possible grammar, there are some pretty wild grammars, and we, for the most part, are not going to try to handle every possible grammar. But there is a lot to be said about this category. They're called the context-free grammars, and actually this includes every example that we've ever talked about. So it's a very general class, although not technically everything goes. So I will tell you what a context-free grammar means. So I'll write this, let's just write a real definition here. G is called a context-free grammar and I'm always going to write CFG. CFG means context-free grammar. What this means is when every production, that is the arrows in the grammar, looks like something like X goes to, S maybe, where X is a single non-terminal, and then the S is any string of terminals or non-terminals. Maybe I should say and. I mean the S can just be anything you want, any combination of big letters or little letters. That's what terminals and non-terminals means, remember? The terminals are like the little letters. That's what you end up with at the end. The non-terminals are the big ones. So what this says is context-free means the left side of every arrow is just one of the big letters. That's it. And the right side can be whatever you want. All right? Every example that we've ever done is of this form. So all our examples are context-free. All our examples that we've seen have been context-free grammar. All right? Something like S goes to AS or BT or epsilon, and T goes to TB squared or BST or A squared. I don't know. I just made that up. But that is a context-free grammar. All it means is the left side must be a single non-terminal. That's what it means to be context-free, which is every example that we've ever talked about. Non-context-free is when that is not true, which is that is technically allowed for a grammar. You could have other things on the left side. So a non-context-free grammar looks like, something like S goes to AS or BT, T goes to ABT or S, and then something like AS goes to SA. This is not context-free, and it's the last one there that makes it non-context-free. The last one says if you have an A next to an S on the left, you can turn it into an A next to an S, but on the right. All right? This one right here, this last line makes it non-context-free. All right? The terminology context-free has to do with the idea is that these rules, of course, these are all substitution rules, and we think of these as substituting. I can change S into AS. That can be done regardless of the context. That is to say, this S, no matter where it is, no matter what is next to it or whatever, you can always do the substitution. S can always turn into AS, or S can always turn into BT. Whereas this one here has something to do with the context. That is to say, we can rearrange the S, but only when it's to the right of the A. That's where the word context comes in. So here, my interpretation of this rule is something like S can move around, but only in some specific context, right? And that's why if you don't have a rule like that, it's called context-free, because none of the rules require any kind of context. What the context in this case is, it has to be on the right of A, right? If the S is to the right of an A, then you can do this rule. The other two rules can be applied regardless of context. They are context-free. You can do them whenever you want. All right. So we are going to focus almost entirely on context-free grammars. That is, ones where the rules have only a single letter on the left side of the arrow. No weird stuff like AS goes to SA. All right. Another simple bit of terminology here is any language. You know, there's a name for a language which can be generated by a context-free grammar. You know, the language of a NFA or whatever is called a regular language. The language of a context-free grammar, any language which can be generated by a context-free grammar is called, naturally, a context-free language. And I'm going to write CFL for that. So a context-free grammar is a grammar, you know, it's a thing with the arrows. A context-free language means some language which can be generated by a context-free grammar, the CFL, all right? Now, we've already seen, like what we did, 10 minutes ago, any grammar can be converted into NFA. No, the other way around. Any NFA can be converted into a grammar, right? It's not true what I just said. Any NFA can be converted to a grammar. This is what we did, at the beginning of class. Any NFA can be converted to grammar. And if you do it according to the way that we did it, these examples that we did way back here, the grammar that you get when you do that conversion always looks like this. That is a context-free grammar. There's no funny business on the left side, right? It's just a single letter. So sorry to scroll away from what I just wrote. Any NFA can be converted to a grammar, and in fact, that grammar that you get will be context-free. So any NFA can be converted to a grammar. Actually, it'll be a context-free grammar. All right? What this means, you can write this as a theorem if you like. That's, more specific than the theorem that I wrote before. It says any regular language is a context-free language. All right? If it's a regular language, that means you can make an NFA for it. And that means you could make a context-free grammar for it. And so any regular language is a context-free language. But the other way around is not true. There are some grammars, some context-free grammars that can give you non-regular languages. All right, so actually, any regular language is a context-free language. The converse is not true. The converse would say any context-free is regular, but that's not true because we have my favorite non-regular language. S goes to A, S, B, or epsilon. This makes this language A to the N, B to the N. Is the example that we talked about last time. That means this one here is non-regular, but it is context-free language, right? It is context-free because I just wrote a grammar for it that is a context-free grammar. Remember, context-free grammar just means the thing on the left is not weird. The thing on the left is just a single letter. All right? So that means that the regular languages, and here's a sort of a picture that I want to encourage you to think about, and I'm going to redraw this very simple diagram many times. What we have is the regular languages. They are sort of a small bit of the larger universe of context-free languages. All right? Every context-free language is regular, but the converse, the other way around is not true. Not every regular language is context-free. All right? And as we go on for the rest of the semester, actually we're going to add in larger and larger categories. All right? From now on, you should think of the regular languages are like the simplest kind or the nicest kind. They are the simplest kind, but they represent just a small a small neighborhood in the universe of languages as a whole. All right, these are the nicest ones, the regular languages. The context-free languages are a little stranger, but not so crazy. All right, and in particular, I'm going to indicate on my diagram a specific language over here would be A to the N, B to the N. That's one which is context-free, but it's not regular. All right. Are there other languages out here that are not even context-free languages? Yes, we'll talk about them eventually, but not today. All right. This sort of description of the languages in increasingly more complex categories, this is referred to as the Chomsky hierarchy of languages. This is named after a mathematician named Noam Chomsky, who actually was the person who invented grammars in the way that we are formalized grammars in the mathematical sense. Chomsky actually is still with us, still living today. Anybody familiar with Noam Chomsky? He was a computer scientist and linguist in his youth. He's now quite old. At least he looks very old when you see him every so often. And you see him because he has in the passing decades turned into a bit of a political radical. He is, I think he describes himself as an anarchist, and you occasionally, I don't know if you see him. I occasionally see sort of viral clips of him on Twitter saying his hot political takes. He has been very influential in politics, although never as like a mainstream. He's American, and he would never be acceptable in mainstream American politics. But people who are sort of on the fringes, shall we say, a lot of people talk a lot about Chomsky in that world. I don't know much about his politics, but look him up. He's old. All right. So what I would like to talk about, we'll do a little bit now and then more next time, is how can you make a context-free grammar for a language? You know, I say a particular language, you give me a context-free grammar. Make a context-free grammar for this language. This is the kind of thing that I want to do certainly for the rest of today and probably all of tomorrow. Language. Make a context-free grammar for this language. This is a typical, homework problem. I describe a language. You make me a context-free grammar for it. For instance, if I say A to the N, B to the N, you say S goes to A, S, B, or epsilon. Now that, I just sort of memorized that, but actually there are some basic techniques that we can talk about which will help you to create that grammar if I describe to you a simple or not so simple language. All right? So basic strategies. There's no general, there's no formula to plug into. There are some basic strategies though that you can apply. So I got strategies. All right. First of all, if the language that I'm trying to, if the language that is described to you is regular, if it's a regular language, then this is easy from the get-go. Then you can draw an NFA and then convert it to a grammar. So that will always work. Now, sometimes it's a pain to draw the NFA, but whatever. If the language is regular, you can make a NFA and then convert to a context-free grammar. All right? Using the procedure that we talked about at the beginning today. And this is always, shall we say, easy. I mean, it might take you a few minutes to do it, but in theory, you can do it this way without much trouble. Okay, so if the language is regular, I consider that to be easy. What if it's not regular? Then there are many different kinds of things that might appear in the language, and I would like to talk about one common feature. So the rest of everything that we're going to say is for non-regulars. One common feature of non-regular languages is often languages which involve, I'm going to call this balancing. Like in, the standard example of that is A to the N, B to the N. And what I mean by balancing is it requires that the number of A's is the same as the number of B's. Every A is matched with one B, or every A is balanced with one B. So here I call this balancing because the number of A's is balanced. Or rather than saying number of, can I just say each A, this is a better way of saying it, each A is balanced with one B, right? And the basic strategy, how do you achieve this kind of balancing in a grammar? So to achieve this balancing, you make the grammar so that the A and the B are created at the same time. This will ensure that there's always a B for every A. If you make it so that the A and the B are created in the same arrow of the grammar, in the same step, every time you produce an A, you produce a B at the same time. So what I mean by that is, well, it's like this. I make one step which creates the A at the same time as the B, all right? And then, in order to make this particular example, A to the N, B to the N, you need to do this so that I put the S in the middle. Now you might think about, what if I put the S on the right side? I could still make the A and the B together, but then put the S on the right side. Then actually it doesn't make that. The S has to go in the middle here so that you can sort of gradually build out all the A's end up on the left and all the B's end up on the right. And then I need to do or epsilon just to make it finish. But this, in terms of thinking about how to make the grammar, this is really the important idea behind this grammar. And this is how you think of it in terms of balancing. You have to create them at the same time. I will say, you might be tempted to say, can't I just do like this? Something like that, where rather than creating them at the same time, doesn't this still work? You make the A first, but because I'm going to T, I have to do the B also. Maybe there shouldn't be a or epsilon here. Maybe it should be there, right? This way, I have to make the A, and then I also have to make the B. But that actually, this will not give you what you want, because the S will be after the B in this case. It's not. Don't do that. I'm going to scribble it out, and then I'll scribble out the word don't again, in case you thought that was a double negative. I scribbled the don't 3 times, which means it's still a negative. All right. This is how you achieve things like balancing. Let's just do some simple variations on that, and then that'll probably do it for today. So A to the N, B to the N. I would just write this again. This is S goes to A, S, B, or epsilon. All right. You make the A. Every A is created at the same time as the corresponding B. What about? How about A to the N, B to the 2N? So, first of all, I look at that and I recognize there is some kind of balancing going on because the power of the A is somehow related to the power on the B. They're not the same, but they both have an N in them, all right? So it's not like the amount of A's has nothing to do with the amount of B's. Actually, they are related to one another. You have to think, what exactly is the balancing that's going on here? In this first example, it's every A has one B that goes with it. Can someone rephrase in this example? Every A is balanced with...
2 B's?
Yeah, every A is balanced with 2 B's in this example. And so, can you suggest how should I make the grammar for that?
C, S goes to A, S, B, B.
Mm-hmm, I like that. Or epsilon, all right? Every A is balanced with 2 B's. Each A balances with 2 B's. Yeah, great. Okay, that's not so hard, right? Let's try, I got 2 more simple variations of increasing complexity, I suppose. A to the N, B to the N plus 1. So again, when I look at this, I see sort of matching ends up there. So that means there is some kind of balancing going on here, although it's different from before. A to the n, b to the n plus 1. I would say there's a certain number of, to explain this in words, there's a certain number of a's, and then there's just like one extra b. Anyone want to, can we suggest how to make a grammar for that? Yeah.
A goes to ASB or B.
Yeah, I like that. A goes to A, S, B, or B. I think the thought process here is the A, it's still the case that every A is matched with a B. It's just like in the end there's one extra B. And that's what this does, right? This extra B. When you finish, you got to just put in an extra B. So I would, to describe this in words, I would say each A balances with one B and then plus an extra B at the end. I mean, at the end of the derivation, actually, it ends up going in the middle of the string, but that doesn't matter. All the B's are the same, right? Each A balances with one B, plus there's an extra B at the end. Okay, great. I got one more. A to the M, B to the N. M is greater than N. All right. Now this one you have to look a little carefully to even tell that there is any balancing at all, because in the formula there, it looks like just the number of A's has nothing to do with the number of B's. They are different exponents there. But it's not really, they have nothing to do with each other. It's just, it says the number of A's is more than the number of B's. How could we make this happen? Anybody got an idea? Yeah?
You do ASB or AS or A.
Okay. I kind of like this idea. I think what he's thinking is, it's kind of like this, right? This one produces one extra B at the end. The way that I would think this through is the M is more than the N. That means the number of A's is more than the number of B's. I could think of that as saying, just imagine the number of A's and the B's, you make them the same to begin with, but then at the end you could just make a whole bunch of extra A's. All right? So the way that I would describe this in words is, I would say balanced A's and B's, but with extra A's at the end. I mean when you're done with the derivation. I don't mean at the end of the string. They will end up sort of in the middle. Balanced A's and B's, but with extra A's. And then, so how would you make that in a grammar? I would, first of all, go S goes to ASB. So that's the basic pattern that you use to balance A's and B's. And then the or here. Now, by now I've forgotten what you said before. Do you remember? Or do you?
I think I said AS, but I'm now thinking that's might not be it because it would go at the end, right?
Yeah, this is not quite right. One problem with this, is it? I think maybe that could work.
Yeah, that'll go in the middle.
I think this is okay. Yeah, this will create A's and B's, the S always staying in the middle. And then you can do this one whatever you want to just make extra A's, and the S will still be in the middle. Actually, you need one more thing here.
Or A.
Or A, yeah, great. You got to stop at some point. Now, typically the way to stop would be to say or epsilon. Although if you put a or epsilon here, then that would allow the possibility that M equals N. You could just not do any extra A's. This forces you to do at least one extra A. All right? I like the looks of that. Actually, this is not what I was going to say. I think it's a little clearer if I were doing this to say something like this. So why I like this, I mean, this is more complicated to write, but to me, the thought behind this is a little bit clearer. The way that I think this through is I can go S goes to ASB as many times as I want. This will create balanced A's and B's. And then at some point, I just switch to this one. And then this one will create extra A's if you want. So this kind of sort of segregates to two stages. First of all, I'm making A's balanced with B's. And then at some point, you switch over to making extra A's here. All right, we're going to do plenty more examples next time. Let me know if you have homework questions.